Now let's first have a look at the normal distribution again. So we said x is normal distributed with the parameters mu and sigma square if its density function was like that. So there's a normalizer times e raised to the power of -1/2 times x minus mu squared divided by sigma squared. And so this was in 1D, meaning that the probability density function looks like that. We have mu here, and then we have this Gaussian bell-shaped curve with inflection points here and here, which are at mu minus sigma, mu plus sigma, and if I draw a random variable, it is with a 68% probability inside this area. So for plus minus 1 sigma, it is 68%, plus minus 2 sigma, it is 95.5%, and for plus minus 3 sigma, it's 99.7%. And so if you look at the exponent, x minus mu squared divided by sigma squared equals 1 if and only if x equals mu plus minus sigma, which is exactly this range. And now if we generalize this, which is in 1D, to 2 dimensions, we will have the following. Now we denote this as sigma x squared plus y minus mu. So this needs to be mu y, and so we will call this mu x squared divided by sigma y squared. And so we have seen if this is 1, this means in our 1D world that we are either here or here. Whereas if this is 1, this now means in our 2D world, where we have mu x here and mu y here, that we will be somewhere between here and here, but also between here and here. So this condition is fulfilled by the points lying on this ellipse. Now we can express this formula in a different way. We see we can write this as a quadratic form where we have a matrix, in this case a 2 times 2 matrix of 1 divided by sigma x squared and 1 divided by sigma y squared on the diagonal and 0 everywhere else, times x minus mu x and y minus mu y as a column vector multiplied from the right and the same as a row vector multiplied from the left. Because this gives the vector times this row vector, which gives the first element times the first plus the second element times the second, which gives exactly this formula, which is the same as this above here. And so now let's have a look at this matrix. So this matrix in our quadratic form, this is our variance raised to the power of -1. So it's the inverse of the covariance matrix, because if the covariance matrix is diagonal, I can obtain the inverse of this matrix by an element-wise inversion. And so we see if our covariance matrix looks like that, then our probability density function will be some normalizer times e raised to the power of -1/2 times x minus mu times sigma raised to the power of -1 times x minus mu, where now we use a vector form and x equals our xy and mu equals mu x mu y. And since we use column vectors, we need a row vector here and we have to transpose this. Now if our probability density function is a vector times this expression, then in 3D it will look like that. Here's x, here's y, and this will be our PDF. So this will be the first component of mu, this will be the second, and our peak will be here. Now this will be our bell shape in 3D. And here we will have the ellipse of the inflection point, which we will usually draw in 2D. And here the PDF extends in all directions to infinity. And this is called the 1 sigma error ellipse. So now let's have a look at that once again. So in our case, our covariance matrix was this, and we obtained an error ellipse like that. So apart from the main diagonal, we didn't have any non-zero entries. And this is the uncorrelated case, where the random variables x and y are independent, because x doesn't tell me anything about y. And so in the general case, our covariance matrix will look like this. So we will have the variances on the main diagonal, but we will also have the covariances off diagonal, which are non-zero, which means that x and y now are correlated. So our ellipse will, for example, look like that. So it will now be turned and look like this. So we will still have this length of the main axis, which will be now here, and the length of the second axis, which will be now here. But these do now not coincide anymore with some min and max points along the axis. So if we want to draw this ellipse, what is normally done is an eigenvalue eigenvector decomposition of sigma, which is a real and symmetric matrix. And so we will obtain a matrix V times a diagonal matrix containing the eigenvalues times V transposed, where V will consist of two column vectors in the 2D case, which are the eigenvectors of sigma, corresponding to the two eigenvalues. And so if we draw this, then if V1 is the eigenvector belonging to a larger eigenvalue, it is this, and then V2 is the eigenvector belonging to the smaller eigenvalue. So let me test your intuition here. So assume I have a bivariate distribution of x and y, which is normal distributed. So C is normal distributed with a mu, which is a vector, and a covariance matrix. And now I tell you that in addition, I know that x is normal distributed with mu, a scalar, and some sigma square, and y is normal distributed, say, with 2 mu. So this is the same mu and sigma square. And now I want to know for this bivariate distribution, how does the sigma look like? So this is sigma x squared, sigma xy, sigma y squared, sigma xy. So does the corresponding arrow ellipse look like that? So it is a perfect circle. Or does it look like that? So its axes are parallel to the coordinate axis, but it is elongated in one direction. Or does it probably look like that? So it is tilted by, say, 45 degrees. And one of the half axes is a little bit longer and one a bit shorter. So A, B, and C. What do you think is correct?